Now I shall start fluid mechanics, very important subject of mechanical engineering as regard to the gate examination, because this subject is very closely and intricately connected to both thermodynamics and as well as heat transfer. In fact, particularly in the convection heat transfer, the applications of fluid mechanics, particularly in the boundary layer theory, viscous stresses and thickness of the hydrodynamic boundary layer, etc., would be vastly done, particularly in the convection heat transfer. So the fluid mechanics subject plays very vital important role in understanding heat transfer also. And also that in the gate examination and also in the IES examination, the number of questions asked from the fluid mechanics are good in number. So first of all, let me define fluid. Definition of fluid. How do we define a fluid? If you take a solid, if you exert a certain tangential or shear stress over the solid, under the action of the great shear stress, the deformation of the fluid is very minute. Once the shear stress is removed, the fluid would almost regain its original shape and size. But if you look at the fluid, it will resist slightly the shear stress, or otherwise fluid deforms continuously under the action of shear stress or tangential stress. So I could define the fluid like this. A fluid is a substance that deforms continuously when subjected to even an infinitesimal shear stress. Whereas solids can resist tangential stress or shear stress at static conditions, undergoing a definite deformation. While a fluid can do it only at dynamic conditions. Undergoing a continuous deformation as long as the shear stress is applied. So the broad distinguishing of fluid and solid can be given like this. A fluid deforms continuously even under the action of the slightest shear stress or tangential stress. In future, we are going to call these shear stresses as viscous stresses. In fact, in the solids, the molecules are very closely packed. In fact, in the fluids, there is a relative motion inside the fluid of the molecules. That is also we can distinguish between a solid and the fluid. Now I shall highlight the important properties of the fluids. Fluid properties. First property is mass density designated as rho. It is defined as mass per unit volume. Rho is m divided by v. Units are kg per meter cube. For example, rho of water is 1000 kg per meter cube or 1 kg per liter or 1 gram per milliliter or cc. Second definition. The important definition, this is weight density, which is also known as specific weight, denoted as small w. It is defined as weight per unit volume. W is weight by volume of the liquid. It can be written as weight, it can be written as mass into acceleration due to gravity divided by volume. Mass by volume we have just defined now as a rho into g. W is rho g. Specific weight is mass density into acceleration due to gravity g. Units of W will be, because it is force by volume, weight is nothing but force, I can write as Newton per meter cube, the units of W. For example, W of water is 9.81 kilonewton per meter cube. Third definition is specific gravity, also known as relative density RD, designated as S. In fact, this is a property of the fluid which compares the densities of the fluids with the density of the standard fluid, that is water. So I can define it as, it is defined as ratio between density of fluid and density of standard fluid, that is water. S is equal to rho of the fluid divided by rho of water. For example, S of mercury is 13.6. It means density of mercury is 13.6 into 1000 kg per meter cube. Density is one of the heaviest fluids we can talk about in fluid mechanics. Density is 13.6 times, mercury is 13.6 times heavier than that of water. Next property is specific volume, small v. It is an important property in thermodynamics also. It is defined as volume per unit mass. Small v is v by m, that is reciprocal of density, meter cube per kg. Specific volume of water is obviously 0.001 meter cube per kg. Next property is viscosity. mu, dynamic viscosity, it is also known as. Though viscosity is a fluid property, the effect of this property is very well understood when the fluid is in motion. In the flow of the fluids, fluid elements move with different velocities. So each element of the fluid will find some resistance due to the fluid friction within the elements. So we can identify shear stress between the fluid layers moving with different velocities. In fact, Newton is the man who has really put up a relationship between this shear stress or tangential stress or viscous stress and the velocity flow field. If you look at fluid layers having different velocities, now this, if u is the velocity of the fluid layer, it is a function of y. Fluid particles are moving in the same direction. Fluid layers are moving in the same direction, but they are moving with different velocities. Suppose that if you take fluid layers at different heights, we find tangential or viscous stresses between them. Now the figure represents the fluid particles moving in the same direction in such a way that the fluid layers move parallel with different velocities. Now, for example, if we take two fluid layers, if this is y, I consider two different adjacent layers of the fluid at a distance y measured from the reference axis. The upper layer, which is moving faster, tries to draw the lower layer, slowly moving layer along with it by means of a force F. Whereas the bottom layer would exert exactly same force but in the opposite direction on the top layer, according to the Newton's third law. For every action there is equal and opposite reaction. Thus, the dragging effect of one layer on the other is experienced by a tangential force F on the respective layers. If F acts over an area of contact A, then the shear stress tau is defined as F by A. Newton has said that this shear stress tau is proportional to the quantity delta U by delta Y, where delta Y is the distance of separation of the two layers and the delta U is the difference in their velocities. In the limiting case, as delta Y tends to 0, where delta Y is the distance between the layers, delta U by delta Y equals du by dy, which is also known as velocity gradient at a point in a direction perpendicular to the direction of motion of the layer. tau is directly proportional to the du by dy. Shear stress is directly proportional to the velocity gradient. Now I shall explain this viscosity in a slightly different fashion. Consider two parallel plates shown in the figure, top plate and bottom plate. The gap between them, I say, let it be y. The bottom plate is fixed, for example. Gap between the plates is y, and this gap is filled with a fluid. I suppose I exert a force of capital P on the top plate, and the top plate is moving with a constant velocity v. There is one layer of the fluid getting attached to the top plate, and hence this layer should move with the same velocity as that of the top plate, that is with velocity v, because that layer cannot slip over the top plate. Similarly, there is another fluid layer getting attached to the bottom plate. Because the bottom plate is fixed to the ground, velocity is 0, that fluid layer also will have the 0 velocity. The top layer is having the velocity v, and the bottommost layer is having the velocity 0. But different layers at different heights will have a different velocities. The length of the arrow is indicating the velocity of the fluid layer at any particular height y. So I suppose u is the velocity of the fluid layer at a height y. So this gap is, I suppose, dy. Now the viscosity could be understood like this. There is tangential shear stress or viscous shear stress between the fluid layers because of the dragging effect. One layer tries to drag the adjacent layer. So viscosity is the property of the fluid by virtue of which there is a resistance offered by one layer of the fluid over the adjacent layer against the relative motion between them. As we have seen in the figure, there is relative velocity prevailing between the layers. Different fluid layers at different heights are having different velocities. Bottommost layer has got 0 velocity, topmost layer has got the velocity v. So the velocity is varying maybe linearly or parabolically or whatever may be the function. The velocity is changing at different heights. Different layers at different heights have got different velocities. So Newton's law states that Newton's law of viscosity states that the shear stress between the layers is directly proportional to velocity gradient or rate of angular deformation or rate of shear strain. This is the Newton's law of viscosity. Tau is directly proportional to the du by dy. Here du by dy is called velocity gradient, that is per second units, and tau is shear stress or viscous stress or tangential stress between the layers. having the units of Newton per meter square. The proportionality constant is given by mu, very important property of the fluid. Mu is known as dynamic viscosity of fluid. What are the units of mu? Newton second per meter square, also known as Pascal second. The dimensional formula for the mu is m L power minus 1 T power minus 1. Dimensional formula. So, viscosity or viscous force is a non-conservative force, just like frictional force in the applied mechanics. Viscous force is a non-conservative force. Any work done against this non-conservative force gets automatically converted into heat energy. According to the thermodynamic laws, the work done against the viscous force gets transformed into heat energy. So, viscosity is a very important property of the fluid, by virtue of which there is a resistance offered by one layer over another layer against the relative motion. The fluids that obey the Newton's law of viscosity are known as Newtonian fluids. The fluids like water, air, mercury obey Newton's law of viscosity and are known as Newtonian fluids. Other fluids like paints, different polymer solutions, blood, do not obey typical linear relationship of tau and du by dy and are known as non-Newtonian fluids. Causes of viscosity. If you look at what are the reasons for viscosity, number one, intermolecular force of cohesion. Particularly in the liquids, this plays a very predominant role. And number two, molecular momentum transfer or exchange. In fact, in gases, where the molecules are placed spatially with a great distance between the molecules as compared to the liquids, the molecular momentum exchange plays a vital role in deciding the viscosity. Due to strong cohesive forces between the molecules, any layer in a moving fluid tries to drag the adjacent layer to move with an equal speed. Thus produces the effect of viscosity, as we have seen earlier. Particularly in the liquids, the intermolecular forces plays a very important role. But whereas in the gases, the molecular momentum transfer during the collisions between the gaseous molecules plays a role in deciding the viscosity. But as the temperature of liquids increase, intermolecular forces of cohesion decrease, hence viscosity of liquids decrease. But in gases, as temperature increases, gaseous molecules move with higher velocities, hence molecular momentum transfer between layers increase, hence viscosity of gases increase. So the mechanism of viscosity is different in liquids and in gases. In liquids it is due to intermolecular force of cohesion mainly, whereas in gases the viscosity is mainly due to the molecular momentum exchange or transfer. So according to the kinetic theory, the gases molecules will move with a greater velocities at higher temperatures. I can expect more number of collisions between the layers per unit time, hence the viscosity increases in gases, but whereas in liquids viscosity decreases with increase in temperature. This is an important point. Both liquids and gases, the viscosity is independent of pressure. Pressure will not play any role. Here only the temperature plays a role. Now I define ideal fluid. It is the fluid having zero viscosity. Mu is 0 for ideal fluid. In fact, all the real fluids, in reality, in all the real fluids will have a viscosity greater than 0. So there is no fluid having 0 viscosity. So ideal fluid is only an imagination or hypothetical fluid having a 0 viscosity. But in future, while writing equations like Euler's equation of motion, Bernoulli's equation of motion, etc., the ideal fluid concept plays a very vital role, making the mu value 0 is, that is assuming the fluid as ideal, is a very important concept in developing equations, particularly in the irrotational flow, etc.